So you have to look at rotating it about this point, and this point. All right, those are the 3 points we have to do. Are you out? All right, see you later, babe. So this is L over 2. Let's do that first. We have the moment of inertia about the center, which is known to be 1/12 ml squared. Parallel axis theorem allows us to move the moment of inertia to any axis parallel to the one through the center of mass. So believe it or not, it doesn't matter that we're shifting it away from the object. This works in 2 dimensions, because it has to be a parallel axis. It doesn't work in 3 dimensions so much, but it works anywhere around the object as long as our axis is parallel. So all I have to do is take my 1/12 ml squared and then add it to my shift distance, which is L over 2 squared. That's it. This one comes out to be 1/3, by the way, for this one, number 1. It's just like shifting it this way. It doesn't seem like it should work that way, but it does. So doing number 2, that one's going to be just 1/12 ml squared plus ml squared, because my shift distance is L. So that's number 2. The one that's a little more is for number 3, that's your shift distance. So you'd have to figure that out. Pythagorean theorem, probably the best way, because it's going to be L over 2 squared plus L squared to the 1/2 power. So that's 1 plus a fourth, or 5/4, is that right? So this will be the square root of 5/4 L squared. Well, nobody's saying no, so I guess so. Just looking at people. All right, so we're good. Or do you want to do the algebra real quick and make sure my arithmetic is right? My arithmetic's right? Or do you want me to do the arithmetic? Oh, okay. I'll do the arithmetic. L squared over 4 plus, I'm going to say 4L squared over 4 to the 1/2. Common denominators. So that's got to be 5L squared over 4. So my arithmetic was good. Solid. So back over here, 1/12 ml squared plus m times 5/4 L squared to the 1/2 squared. Just writing it all out, really, really crazy like. So it ends up being 1/12 ml squared plus 5/4 ml squared. We'll need common denominators. And in this case, 1/12 ml squared plus 15/12 ml squared. So I get 16/12 ml squared, which is 4/3 ml squared. Yeah.
For the third one, could you just do from the end and use 1/3 ml squared as your...
The parallel axis theorem requires that you shift it from the center of mass. So, there might be the possibility that the numbers work out. It would be accidental. And I say that because it is plausible that doing it from the end would give you the right answer. But
just from the looks of it being 4/3, I think it works out that way.
I think so too, because it's like shifting this way and this way.
Yeah.
But I know that for other shapes that won't work, so I'm afraid it's just coincidental. Or just, trick of the numbers. I didn't record hardly any of that. Well, anybody just joining us, you're in trouble. Don't care. They should be here in class. We're using a ring, but we've had the center of mass, we have the axis of rotation shifted to the edge. So we're going to start with the moment of inertia of a ring, but we're going to add to it m times the shift distance squared. I'm not going to write out shift distance much longer. I keep doing that because eventually I'm just going to write mx squared or mr squared, and you're going to say radius, and I'm going to look at you and say, no, it's not radius, and you're going to be confused. I keep writing shift distance in there purposely because I think on your equation sheet they have an r there. Like they say something like moment of the center of mass plus mr squared, and that is not radius yet again, but we've run out of letters apparently. So I'm putting shift distance in there every time as we practice so that you are reminded that this is how much we are shifting the axis of rotation from the center of mass to wherever the new axis is. And in this case, that's the distance of 1 radius. So it takes the moment of inertia and effectively doubles it. So I get mgr equals 1/2 times 2mr squared times omega squared. And that's how you get omega. So omega is going to be, let's see, we can cancel out the m's. We can cancel out the 2 and the 2. And I can cancel out one of the r's. And I get omega is the square root of g over r. Any questions? Now, if you want to do this for the disk, the problem is the same, except you start with 1/2 mr squared here. That's how you do the problem for the disk. Right? That's the only difference, is that the starting moment of inertia is 1/2 mr squared for a disk and mr squared for a ring. That's going to give you a smaller moment of inertia here. It'll be 3/2 and not 2. And because it's 3/2 and not 2, you're going to get a slightly different answer here for your speed. It'll be faster because that particular thing is easier to turn. All right. I didn't answer question A, but question A is to find the acceleration. So net torque equals I alpha. And for this part, we're only interested in when it's pulled to the side and initially released. So although we've got all this, we're interested in just this moment when there's a unbalanced force acting at the center of mass. It doesn't matter that there's no actual object at the center of mass. We still treat the center of mass as the center of gravity. This distance is r, so my torque is going to be r times mg times the sine of 90 degrees. That's how much torque there is. There's only one torque. There's a force on the pivot point upwards. It's equal to mg as well, because at that instant, the net force is 0, but the net torque isn't. So we don't need that force, though, because this force can't apply a torque to the object because it's acting at the pivot point. Okay, I alpha, so we just did I. It's 2mr squared times alpha. So you're just solving that for alpha. Again, m's cancel. One of the r's cancels. And that's all that you can cancel. So alpha is going to be g over 2r. And it'll be a greater acceleration if you do it for the disk, because it has less moment of inertia. So although there is, the rest of this is like all letters and and algebra, having this angle adds a bit of a numerical component, which is a little arbitrary, but let's just say square root of 2 over 2 is what you're going to be using there. You don't have to do that. You can do 0.707 if you want, but it's just whatever the sine of the angle is. So I would leave it to square root of 2 over 2. If for nothing else, you have other fractions in there, and that might make doing the other fractions easier. But this is going to equal 1/3 ml squared times alpha, and you solve that for alpha. All right? Keep going. All right, so next, MGH equals 1/2 I omega squared. This is a conservation of energy problem, just like the ring held to the side or the plank held to the side. However, H, we need to take issue with H, because in this case, H is based on, why does it keep doing that? H is based on, stupid. Well, there we go. Trying to straighten it so it looks just right. This distance from here to here. Now, I've given you guys methods to find this distance. You'll need to use them. For this problem, it's H equals L over 2, because it's got to be this distance, times 1 minus cosine 45 degrees. Any question about where any of that came from? All right. So, mg L over 2 times 1 minus cosine 45 degrees equals 1/2 1/3 ml squared omega. There's something pretty here. Yeah, you could say that this is 2 minus the root of 2 over 2. But there's nothing pretty inside there. If you want to drop it down to 0.3 or whatever it is, fine. Because it's not going to come out to be something nice and neat and convenient. If you know what I'm saying. But the rest of this problem plays the same way as before, although it's not omega, is it? It's omega squared. I just can't fit my little pencil over to the side there. So there, omega squared. Now, is there anything else about this problem you want me to speak to? I think I should speak to at least one thing. The last question asked for the tangential acceleration at the bottom. Now, it doesn't pick a place, does it? It just says, what is the tangential acceleration? When the rod passes the vertical. So when the whole rod is vertical, tangential acceleration has to refer to a place on the rod for one thing. Because the rod isn't experiencing any angular acceleration, there's no place on the rod experiencing a tangential acceleration, because the tangential acceleration is the angular acceleration times a distance from the pivot point. This is the expression for the tangential acceleration. So although we could figure it out for some point on the rod when we first release it, because each of these points has some amount of tangential acceleration. Remember, this point started from rest and speeds up to some velocity when it gets here. The fact that the angular acceleration is 0 at the bottom is the reason why there is no tangential acceleration anywhere on the rod. But be careful. This is mechanics. Mechanics is going to ask these questions. But it's also going to ask, what is the radial acceleration? If I want to trick you, I play with these two words to see if you know what they are. It's not obvious, but this is how you get the tangential acceleration. And it may not be obvious, but this is how you get the radial acceleration. It is the centripetal acceleration. So it's going to be v squared over r, or omega squared times r. And for this problem, this r and this r will be where the center of mass is. That's how we found the net force from the pivot point, or on the pivot point, yesterday. Or the day before yesterday. Is that good? Okay.